Hello. So I'm going to start on set 17, our final webwork set of this semester. It's about linear homogeneous systems of ordinary differential equations. And in particular, what I'm going to be talking about is how to solve d dt, the time derivative of y, a function of t, a vector function of t, equals matrix A times y, where A is a constant 2 by 2 matrix. And by constant matrix, I mean it's not a function of t. It's not A of t. And it's homogeneous because there's no added vector function of t on the right. Or, right, if you had a constant added on the right, that would also be non-homogeneous. So one of the things is this differential equation always has the solution y of t is the zero vector. That's the solution to this linear homogeneous ODE. This problem comes in many forms. A lot of the webwork problems have these different notations. We might say y vector prime instead of dy dt is written as this matrix times the vector y. And then often an initial condition is given, y of 0 is 1, 0, or something else. Many of the problems have x as a vector, but they don't put an arrow over the top. So this problem says dx dt, but you can tell from the context that x has got to be a vector because dx dt is this 2 by 2 matrix times x. So that only makes sense if x is a column vector, a 2 by 1 column vector. Some of the problems, like this, look like this. They're just given as a system of two first order ODEs that are linear in the dependent variables. And there's no terms that don't have the dependent variables. I didn't add like a t here, didn't add a 7. Okay. So there is a problem very much like this. So that can be written in terms of a 2 by 2 matrix M, which would be M11, M12, M21, M22 would be the matrix M. And then similar to that, I'm going to be talking about the app we have on the computer, the direction fields and slope fields app, that you enter the differential equation this way. dx dt is a times x plus b times y. Or you can put any function you want, but we're going to be dealing with a times a constant times x plus a constant times y for dx dt, and similarly for dy dt. And here x is a scalar, you can tell from the context, whereas here x is a vector. Okay. And as I say here, problems 1 to 9 are all of this form. They have lots of different notations, but they all can be thought of as dy dt is ay. And then there's a few problems at the end that are a little different. We'll be talking about them. So let's just start with this. How do we solve dy dt is ay? And we might as well also put in the initial condition. Y of 0 is some given vector y sub 0. Okay. Well, step 1 is you find the eigenvalues and eigenvectors of that matrix A. Find the E stuff, the eigen stuff of A. We're going to call it lambda 1, lambda 2, and V1, V2. So it's a 2 by 2 matrix, so there are two eigenvalues. Maybe they're this equal to each other. and then there's eigenvectors. There might not be two eigenvectors. We've had that example. All right. Step 2 is find the general solution to dy dt equals ay. And this has constants c1 and c2. And then step 3, you set y of 0 equals y naught, the vector. And then this is two equations for the two unknowns, c1 and c2. Solve and substitute back in. Okay. So it's very similar to the technique we had for like a second order single ODE. There, for a single ODE, we'd find the characteristic equation. We're going to get a characteristic equation for the matrix here. We get the general solution, which had constants C1 and C2. Plug in the initial conditions, you get equations for C1 and C2. All right, so I want to be more specific about how to find the general solution. Okay, so if lambda 1 and lambda 2 are real, and distinct, in other words, lambda 1 is not equal to lambda 2, then the general solution is y equals c1 e to the lambda 1t v1 plus c2 e to the lambda 2t v2. All right. So let's ask ourselves why this is the case. Okay. So what we're going to do is we're going to just try the solution y is e to the lambda t v for some scalar lambda and vector v. We're going to just going to try a solution of this form. So it's going to be, we're going to have a vector in our two dimensions, our two-dimensional vector, and that just gets multiplied by either a growing or decaying exponential, e to the lambda t. Just plug that into the differential equation and see what happens. And that's the vector y. So vector y is that. So what is dy dt? Dy dt, well, that's a constant. That's a constant vector. The only function of t here is the e to the lambda t. So I differentiate e to the lambda t, I get lambda e to the lambda t v. This is the ddt of e to the lambda t. So plug that in. And you get lambda e to the lambda t v that's dy dt is equal to a, well, I plug in e to the lambda t v. But that's a scalar, e to the lambda t is a scalar that comes in front. This is e to the lambda t v. All right, so e to the lambda t is a scalar, and it's never zero. Right? E to anything is a positive number. So that way, in order for this to be true, you need to have lambda v is, oop, I forgot the a here, is a v. Okay? So, in other words, if I choose lambda just right, and if I choose v just right, I can get a function of this form that solves a differential equation. And this is what the lambda and the v have to satisfy. Does that look familiar? Yeah, that's the eigenvalue equation. In other words, lambda is an eigenvalue and v is an eigenvector. If lambda is an eigenvalue and v is an eigenvector, then this is a solution. Okay? And so is this times a constant. All right. So if I have, and I can also add two solutions to this linear homogeneous ODE and get a new solution. So at least you can see that we get y1, we'll call it, is e to the lambda 1 t v1.
But they're two each.
And y2 is e to the lambda 2 t v2 are solutions. All right, so the general solution is the linear combination of those, provided those are linearly independent. Now there's a problem if lambda 1 equals lambda 2, there's a problem there. And if v is a vector of complex numbers, we have to deal with that later. So later we'll deal with the two problems of lambda and 1 and lambda 2 being complex conjugates, a plus or minus bi. And we'll also have to deal with the case of lambda 1 equals lambda 2, and there only being one eigenvector. But from almost all of the problems in the web work, we have that situation. So again, if lambda 1 not equal to lambda 2 and both real, the general solution is y is c1 e to the lambda 1 t v1 plus c2 e to the lambda 2 t v2. All right. If lambda 1 equal a plus bi and lambda 2 equals a minus bi, then we do something different. And if lambda 1 equals lambda 2, we do something different. All right. So now you're ready to do more than half of the web work problems, okay? Problems, as I mentioned, problem 1 through 9 are all something of this form. The variables might look different. I might have dx dt or something. So you can go through and compute the eigenvalues and eigenvectors for all of those cases. And most of those fall into this first case. Okay? And if they don't try to go any farther, but you can do all of the web work problems when you get real and distinct eigenvalues. All right. Well, I'll come back for the next video and do an example that looks like this with real and distinct eigenvalues. All right. Well, goodbye.